it's recording now. So we are very happy to have Christian Schaffner tell us about the basics of quantum cryptography beyond QKD. And this is, yeah, so I'll just hand over the mic to you.
All right, thank you very much. Well, I'm happy to get the opportunity to recycle some of the stuff I had lying around, and also like tell you a little bit about quantum cryptography. And the reason why there's a beyond QKD here in the title is that most of this material here is based on a tutorial talk that I gave at QIP. So QIP is the Quantum Information Processing Workshop, which is basically kind of the theoretical computer science side of quantum of the quantum computing world. And they always have like 2 days of tutorials before the conference, and I was giving one of those. And that's also, it was 2 years ago in Delft in 2018. And so most of the stuff I show here is kind of maybe say 2 years old. So some of that is slightly outdated. In particular, like some open questions have been solved and some of the focus has shifted, but I try to point out these things. So yeah, and whenever you have questions, please ask immediately. I can see the chat, and I can just unmute yourself and ask a question. I guess we keep this on a rather informal level here. So what I did when I was asked to give this tutorial, I did this. So I kind of wrote everything I know on my whiteboard about quantum crypto. And I also asked people from my group, I guess, I hope you can see it. You can see my mouse pointer as well. I see some people nodding. To kind of contribute. And yeah, if you try to make such a mind web, it's quite a, this was quite a mess. And so I tried to structure this a little bit, and you will see that coming back in the talk. I also want to point out one of the resources here. You're gonna come back to this picture. It's a survey article that I've written together with Anne Broadbent, and it's now from 2015. So, but still, it contains some of the classics, also some stuff I'm gonna talk about in this talk, and it's aimed at you guys. So it's aimed at computer scientists. So it doesn't require much quantum to start with, but it's not written for physicists, but I think you are the target audience of this, and you can just find it on the archive. And you can also actually find the slides and almost everything on either my homepage or on the archive. So this is something I can recommend you to look at. Then another thing I will quickly want to mention is the QCrypt conference series. So that's not QIP, but it's kind of the small sister of it, Quantum Cryptography Conference. This year will be the 10th edition of the conference. It has kind of a similar format. It's going to be organized. I'm co-organizing it together with Serge Veer in Amsterdam. At the moment, it's very unlikely that it can actually physically take place because it's planned for the beginning of August. But if not, so I think actually today is the submission deadline. But if not, we will hold it electronically, virtually, as many conferences do, like QCrypt, for instance. It will be online. So we kind of look at what they are doing and see what the best format is to do these things. And then we will probably organize it physically next year. Still in Amsterdam, so we can recycle a bit of the work we already had. So the series has been started by Matthias Christandl and Stephanie Wehner in 2011. So this year is going to be the 10th edition. It has approximately 100 submissions. Some of them, like a third, accepted as contributions. Last year in Montreal, there were about 300 participants. And the goal is to represent the year's best result in quantum cryptography. So in general, if you're interested in kind of this area, then it's a way to kind of see what's going on in these areas by looking at the program of QCrypt over the last years. And so one of the goals is also to bring together like theory and practice. And experiment really means like physicists that implement protocols. And this is often related to quantum key distribution. So most of the implementation knowledge is in quantum key distribution. Then there's also tutorials and about 6 invited talks. So, and again, these tutorials are actually a good resource for you if you want to learn more about a particular topic. Then looking up old QCrypt programs and the tutorials that were given there, that will be a helpful things to do if you want to know. And most of it should be on YouTube. Otherwise, let me know if you have trouble finding something. I have some backups of old sites as well if they don't exist anymore. All right, so that's more high level information. Let's get back to this picture. And also thanks to the people who helped making it. So what I did is I tried to make kind of a mind map in a more systematic way. And this is something that you can download here on this GitHub repository. It's made using a tool, and even the tool still exists. I figured out yesterday, so fortunately you can still edit it. And what I tried is basically I put some stuff in boldface. So this is maybe a bit hard to see on this small screen, but you can just download the picture and see. So those are actually experiments. This is stuff that has been implemented in practice. And then also in green, I have some open questions. So this was goal of this tutorial was also to kind of show some open questions to the researchers in the field. And some of them have been answered in the meanwhile. So that's actually kind of fun, at least for me it was fun, and maybe I will do this in more detail, kind of to go back and see what has actually been addressed in the meanwhile. Of course, the one area here is post-quantum classical crypto. So that's basically where most of you are at home. And so I'm going to focus on other parts, and I think, well, you can feel free to contribute to that if you want. But somehow there's like the big kind of clouds in this picture is the area up here where we talk about quantum advantage. So this I kind of coined that term before it was used in the context of the supremacy claim. So this is it's more in the sense of like, what can quantum offer which we cannot do classically? So it's in that sense, and in the crypto world, we often talk about like information theoretic security. So this will be the first part of my talk as well. For instance, quantum key distribution is something that we can do if you use quantum communication, but which we don't know how to do if you just allow classical communication. And so that's kind of one big cloud up here. So it includes QKD, it includes quantum money, device independence, some fun stuff I'm going to touch on. Then down here I have a cloud of like quantum data. So that includes kind of secure computation, multi-party computation, secure two-party computation. I'm going to cover that in this talk as well. But also stuff like delegated computation, like how to operate, how to encrypt quantum data, how to delegate the computation to a quantum server. So there's been a lot of progress in this area since I made this graphic, basically. So in the last 2 years, there's been a lot of development here. And then there's a whole box up here in tools. So this is just a bit of a collection of other areas that contribute towards quantum crypto, but there are maybe areas on their own. And there as well, there have been quite a lot of developments with new tools coming up, allowing to do kind of more stuff. And then, of course, there's the whole post-quantum crypto area, which is very active, which you probably know more about than I do. So that's kind of the big picture. And now I'm going to go over some of these sub areas. Yeah, and if you have any questions, then just let me know. So the first thing I want to zoom into is like this area up here, and in particular the one of quantum key distribution. So maybe we can have a quick vote on like say who would be able to describe the BB84 protocol for quantum key distribution to us. So maybe you can use your yes and no buttons in the participant window, so I can maybe everybody can see it actually. If you go to participants, I guess you have some green and red buttons. and he could say, yes, I would be able to, or we not raised his hand. You can say, yes, I would be able to describe the BB84 protocol, or no, I would have no idea how to do this. I don't see any. Maybe you can only raise your hands.
Yeah, sorry, where are the red and where are the options?
Yeah, where are those? Do you, Dakshita, know? I only see a hand. Is this a setting we need to?
Let me try to create a poll. Let's see. I had a question.
Usually we have these buttons, no? At least in my, maybe they've been disabled. And I tried yesterday, there were.
So the question is, can you describe?
Okay, you can raise hands. That's also, I mean, for just yes and no questions, you can.
It's under reactions. Just do thumbs up. Thumbs
you have.
down.
Okay, you have reactions.
It's down there in the bottom. Invite participants, share screen, chat, record reactions. At least for me.
But there are only two options to vote up and clap. There is not no option.
Christian, are you going to test people who say yes?
Well, where should we see this then? I only see people raising hands in the participants list.
We can take that for a yes for
and
now.
I can lower all hands. It's too bad. It's really kind of limited the interactions. Oh yeah, okay, I see a thumbs up. Okay. Yeah, I see some clapping and some hands up, but that means like 4 out of 19 would be able to describe this protocol. If I take it, if I take this poll, then maybe I can lower all your hands. Is that lower all hands? Yeah. Okay, at least that worked. All right, so I will describe it to you. That's, I guess, the purpose of this talk. And for that, I just need a little bit of formality, but this stuff, I guess you have seen. So what I usually do, I just use 2 different colors like yellow and red for these the two bases. So this is what you've seen as computational basis. This is the 0 state. So in terms of vectors, this is just the 1, 0 vector. And the 1 state is the 0, 1 vector. These are basically denoting the 2 directions you can have. And in QKD and often actually in quantum communication protocols, you can really think of them as the direction of the polarization of photons. So you take some light source, and you put the polarizing filter. This is really nothing spectacular. It's really just, say you take a laser and you put your sunglasses in front of them. And just the way you hold your sunglasses is basically polarizing, letting light through that is only polarized in this way. And then, of course, you can turn your sunglasses, and depending on the angle you put it, you can have different quantum states. And the difficulty to do it in practice is that you have to use single photons. And so that then it becomes quite annoying also to detect them. But in principle, just like sending a lot of photons is very easy. You can do it at home. And so then in this red basis, like the diagonal basis, then we have this state is the superposition of 0, 1. So this is that 0 plus that 1 over square root of 2 renormalized. And that's if you kind of do the linear algebra, well, you get this diagonal direction. And you can, if you subtract the 2, then you get the other diagonal direction. So global phases don't matter. And that's why the arrows point both ways. So these are the basic states I think most of you have seen, I hope. And what you can do with them is measure them. So if you do measurements, so we will denote this here as a measurement in a computational basis. Say if you take the 1 state and you measure it, then the outcome is a classical bit. And in this case, it will always say that the outcome is 1. So with probability 1, you will get outcome classical 1, and nothing will happen to the state. And more interestingly is if you take such a state in the yellow basis, and you measure it in the wrong basis in the other one, well, what's going to happen, what you've seen is that with probability 1/2, you're going to get a 0, and the state is actually changed to the one that you observed. So the state has changed to what you've seen, namely to that. And with probability 1/2, you get a 1, and you changed it to the other state. So So am I okay with assuming that people have seen this before? So the basic.
Yes.
Yeah. Okay. So and that's more or less what we need. Then of course you can operate on this quantum states by doing unitary operations. An example of it is the so-called Hadamard operation, which just kind of transforms the from one basis to the other. So the Hadamard is kind of, well, it's a particular rotation you do, but for instance, if you apply a Hadamard gate on this zero state, you end up in the zero state in the other basis. And it's self-inverse. If you do it again, you will flip back to the other basis. So that's the quantum operations unitary transforms that you can do. Now for quantum crypto, a very crucial ingredient is the so-called no cloning theorem. So the no cloning theorem, it says the following. It says, take one of these 4 states at random. So just pick, flip 2 bits and kind of pick one of these states at random. Let's denote it as this question mark. And we try now to make a perfect copy of that state. So basically you want a cloning machine. So this is Dolly, the sheep that we know how to clone. And we would just want to have a machine that kind of makes a copy of these 2 states. Now, and the no cloning theorem basically says that we are not allowed to do that. So we cannot perfectly clone a quantum state. And the proof of this is very simple. I'm going to show it to you on the next slide. Basically, it's because copying is a non-linear operation. So have you seen this as well?
This was an assignment problem in one of the.
Very good. So for those who did not do the assignment, here is the solution, because there's a very simple proof, at least for the perfect case. So here's how you can prove it. So assume such a cloning machine exists. So assume a unitary transformation such that for any state you put in, if you apply this unitary to that state, so here you have this state and you have some helper qubits, some auxiliary qubits, just to as kind of a placeholder, you initialize it with 0, but you want that in the second register, you end up with a copy of that state. So a perfect cloning machine would do this. It would map any state into the state itself plus a copy of it in tensor product. So, and then we want to find a contradiction to that. So in particular, if you do this on the 0 state, well, then you're gonna end up with 2 zeros. If you do it on the 1 state, then you would end up with 2 ones. So that's what happens if you copy either the 0 state or the 1 state. And now we do it on the superposition of these 2. So by linearity of view, so quantum operation always has to be linear. If we try to copy this state, 0 plus 1, and now I always left out normalizations, which sometimes at the beginning is very confusing to beginners, but somehow it doesn't, it helps not to clutter the notation, but in principle you would have to normalize this by dividing by the square root of 2. But if you apply that here, then you can put u here and u there. So you get u of the first part plus u of the second part. And now we just know what you should get because we've done this above here. So you should get a copy of 0 plus a copy of 1. But that unfortunately is not the right answer. So this is not the state that we want because this is a copy machine. So what we actually want is that you should end up with a 0 plus 1 tensor a 0 plus 1. But if you kind of multiply this out and using the properties of the tensor product, you will not only get these 2 terms here that you get by linearity, but you also have these kind of cross terms. And so these 2 states are really very different from each other. And so this is a contradiction because this contradicts our assumption that u was actually copying any state psi. We showed that if it does copy 0 and it does copy 1, well, then it does not properly copy 0 plus 1. So if it works in one basis, it cannot work in the other. And that's a very typical thing in the whole quantum world, that somehow you always play with this complementarity of this basis. Note, for instance, that this actually says that, well, you can have a copy machine as long as you only do it in one basis, in a computational basis, because then everything is classical and you can actually make a copy out of a classical bit, and we do it all the time. But if you have something that works perfectly in that basis, well, it cannot work in the other bases if you have to respect linearity. And so we have a problem here. And this shows that at least a perfect copy machine is not possible in the quantum case. And of course, one needs to use quite a bit more refined methods to actually use that in practice, but somehow in spirit, it's really that kind of enables a lot of quantum crypto, as you will see now in the coming examples. Yes?
So Kristen, this is Vinod. The question: can you show a robust version of the no cloning theorem in the sense, you said that if I know that the vector is in the standard basis, and of course I can clone, right? But if I know that it's close to the standard basis, in some sense, like the angle between the state and the standard basis is small, then can I sort of clone, and how well can I clone?
Yes, you can, all of it. So there are it works up to some degree. So there are approximate cloning machines, and you can say, you can specify exactly how well they do. So there's trade-offs for like if you do that well in one basis, then you cannot do that well.
Got it. Okay. Got it.
And this you can fully specify.
Yeah.
But it's not, well, so even if you know that exactly, it's not the tool that you're going to use, say, in security proofs often. You kind of you use other tricks. In the end, you of course also refer to the linearity of the quantum operations you're allowed to perform, but there are kind of better suited tricks to show security.
Okay.
But of course, people have studied just from a physics point of view, like how well can you actually cone? So yes, you cannot do it perfectly, but you can do it up to that degree. But often these things are not very useful to actually do as a tech.
But can I ask something?
Sure.
But maybe you cannot use it for security proofs, but you may use that as an operation in a cryptographic system, cloning approximately. If the cryptographic tool calls for that.
Yeah, I mean, that's an idea.
It hasn't been done?
So you would kind of try to exploit it as a tool for the honest player, say.
Yes.
No, I'm not aware of it. Often, maybe that's also something we're going to see a little bit back later. Especially if we want to map it back to the classical world, we really want kind of close to perfect correctness. Now in crypto, we want our correctness errors, maybe even security errors, to be negligible, ideally. And that's often not what we get from the quantum case. So which makes it, which renders it kind of useless, or at least unclear what you can do with it.
Depends on the application.
Yeah, depends on the, of course, yeah. It's always, yeah, indeed. So if you kind of define the application to be okay with this kind of error, then fine, yes.
Or maybe even desire this kind of error.
Yeah, I'm not aware of an application of that, but
so in the application of quantum money, wouldn't you care, I guess, about like precise bounds on this kind of thing? You don't want the adversary to be able to quantum state that like will pass verification with some probability.
Usually you want something that where you have some type of parallel repetition property where you're okay with some error, but then you just do it with many qubits in parallel, and then the error goes down exponentially.
Right.
But that's often very hard to show. So this I will also come back to.
Okay. I mean, I'm thinking about more sophisticated, maybe cryptographic type of operations. I don't know if you want deniability of some sort, maybe, or even if you want to do an oblivious transfer, that would not be useful.
I think I will talk a little bit about bit commitment and oblivious transfer later.
Okay.
Yeah. Let's see. All right. Also, so in terms of time, I think I will just go as slowly as I can and try to make it as clear as possible. And then if we're out of time, we can move some stuff to next time. That seems to me the right strategy. I hope. Okay. So QKD. So if you haven't heard about it, then it's really like, it's kind of the elephant in the room, at least from a physics point of view. That's the thing that people care about, what they implement. So I want to spend some time at least telling you what it is. And I'm going to show you the BB84. So the BB stands for Bennett and Brassard 84 version of it. So how it works on a very high level is basically Alice sends some qubits to Bob. And these qubits are really just picked at random from the 4 states we saw before. And then after that, they communicate classically. So this dashed line here is a quantum communication going from Alice to Bob. And then there's some classical communication going between them. And in the middle sits the eavesdropper, Eve. And she has full control over the quantum line. So she can interfere with the quantum communication. But she can only listen to the classical communication. So the classical communication is authenticated. So she cannot tamper with it, but she can listen to it. So that's the kind of setting. And the goal is to generate keys. So these are classical keys, such as classical strings that are identical, and Eve has provably no knowledge about it. So that's basically it. So that's kind of what it achieves. So it offers a quantum solution to the key exchange problem, which does not rely on computational assumptions, because one can actually mathematically prove under the assumptions that I mentioned that really the information theoretic knowledge that Eve has from the tampering with this channel and from listening to this classical communication is negligible about the string that Alice and Bob share in the end. And as I already said, really the important caveat here is that we need authenticated classical communication. And otherwise, for instance, you can just do like in classical Diffie-Hellman, you can just play the man in the middle. So Eve can pretend to be Bob towards Alice and pretend to be Alice towards Bob, and then just like do the standard man in the middle attack. There's no way to prevent that using quantum. But and then the question is, of course, how do you do this? Like, how do you get the authentication? And so what people do in practice is they just use, so either you can do information theoretic schemes, but then you need to start with a key to start with. So they have to have some pre-shared key, which then by using quantum key distribution basically expand. So if it works, you will see, I will show in more detail how the scheme works, but somehow if it goes through, you can show that they end up with more key than they started with. But of course, because Eve has full control over the quantum communication, she can just cut the line or introduce a lot of errors. And then basically they will only figure that out while doing the classical part. And thereby Eve can basically force them to run out of this pre-shared key. So that's a problem that just is inherent to the setting. What you can also do is just use computationally secure authentication schemes, just the digital signatures. And then, of course, the whole security properties of the scheme is kind of downgraded to the computational security of the digital signature scheme. However, it has the advantage that you have to kind of break the digital signatures immediately while this protocol is run. So it's something that you cannot kind of store and then break in the future, because if the protocol has worked, then the information theoretic security holds. So it's what people have called everlasting security. So somehow it's at the moment you need the computational assumption, but if it has gone through and the players can verify that, then the security of the keys is forever. Then you're allowed to give the eavesdropper an unbounded computational power. And even in that case, they will not be able to kind of figure out what the key is. So that then you're kind of safe in the future. And this is basically the main selling point of QKD. So this is what QKD does. It's able to kind of turn a computational assumptions that has to hold at the moment into something that will hold forever in the future. So that's kind of the cool thing that you can do with QKD, which you can actually prove that you cannot do this if you only allow classical communication. So that's why it falls in this area of kind of quantum advantage. That's something you can do in the quantum world, but you cannot do in the classical world. Any questions at the moment about, so I'm going to give some more details how this protocol actually works. But this is just, this was on the high level kind of what it achieves. Okay, so how does it work? Well, you actually do exactly what I said before. So what you do is you pick one of these 4 states, and how it's usually described is Alice chooses a basis string. So think of it just as a random bit string. So either red, yellow, yellow. And then you also pick kind of the bits you want to encode, another independent random bit string. And then you do this encoding. You encode the 0 into the red basis, and you code the 1 into the yellow basis, and you end up with these qubits. So basically you just individually picked one of these 4 states by choosing these 2 bits. And that's the thing that Alice sends over, basically bit by bit, qubit by qubit to Bob. So now Bob, he doesn't know what this basis is. Now we just picked at random by Alice. And also from these qubits, you can actually not see kind of what color they have. So this is a property of the quantum state. So I don't know if you've seen that, but it's, if you receive those and the basis has been picked at random, there's no way for you to figure out what that basis is. In fact, if you picked one of these 4 states, then to you, to Bob, it looks like the completely mixed state. So that's kind of the way you would prove that Bob doesn't know anything about these bits, about these qubits. So what he does is just picks another random basis string. So they might match the right color, but it might also not. So he just picks a random basis string himself and measures in that basis. So he does measurements of these incoming qubits in these bases. And what happens, he gets some outcomes, which is just, again, a classical bit string. And if the basis was correct, so for instance, in this third place here, he measured this red qubit in the red basis, well, then he gets the same outcome as Alice was encoding at the beginning. So whenever the basis matched the right color, well, then he gets the same outcome as Alice had. But whenever they was wrong, we saw before, you would just get a random outcome. Now, if you measure a yellow qubit in the red basis, you will get a random bit. And sometimes this might match what Alice has sent, but sometimes might not. But he doesn't know that yet. So what they're gonna do is now, classically, Alice tells Bob what this basis was, not the bits that she encoded, but just the basis she used. And now they can compare. Now Bob can just say, see, in these first 2 positions, I used the wrong basis. Roughly half of the time he was lucky and guessed the right basis, half the time he did not. And then he just tells Alice, look, these first 2 positions, let's forget about those because I didn't measure in the right basis. Again, he doesn't say what he obtained or so. He just said, oh, in these first 2 positions, our basis choice didn't match. So we have to forget about these positions. So just throw out, so basically half of the positions. And you end up with a string where you know that you were using the same basis strings. And therefore you also ended up with the same classical bit string. Notice that both Alice and Bob here are honest now. So they are basically playing together against the eavesdropper. So there's no like, oh, what if Bob cheats or so on, because here just to have 2 honest guys playing against the eavesdropper. So in principle now you can, so this is what we call like kind of the raw key. And basically you can now use those as the key, but of course it's not that easy because there's also the eavesdropper. So the eavesdropper, he has she has control over this quantum communication. So of course they just compared the classical bit strings, so that part remains the same. But it could be that the qubits that arrived up here, Bob, are not actually the ones that Alice sent. So it could be that there's additionally some errors in this whole procedure. But notice, however, we can already see that from Eve's point of view, these are basically these unknown qubits. Where it was picked, these qubits were picked at random out of the 4 states, and now basically the no cloning on a very high level, the no cloning theorem applies. She cannot simply make a copy of these qubits. Because they are unknown qubits to her, she cannot classically. That's kind of where the difference comes in between the quantum communication and the classical communication. If this was just classical, as an eavesdropper, you can simply make a copy and then just do whatever this Bob does, and there will be no way to generate a key from this. Quantumly, you don't know. Right? You cannot make a copy of these qubits that fly by, and in fact, if you try, then you will introduce errors. That's kind of the crucial point. So if if you try to make a copy, and that's actually the kind of the trade-off maybe also that Vinod was hinting at. So even if you try to kind of get some information out there, what you do is you introduce some errors in the qubits that are sent, and that's something that the honest players can check. So in fact, the quantum key distribution goes on, and they basically kind of do some additional checks. So there's some more classical communication going on between Alice and Bob, where they basically compare some more positions of the remaining string, whether it agrees. So they basically do some checking of how many errors were there. And that also means they will have to sacrifice some more positions and then use error correcting codes. So these are just classical error correcting codes and classical privacy amplification to basically get rid of whatever Eve's knowledge was. So maybe even concretely, and then from that you can extract the key. Even more concretely, maybe because some of you might be familiar with this. So this is just basically information theoretic key agreement protocols. You start basically at that point, like before, maybe around here, you have actually some shared information between Alice and Bob, and Eve has some quantum side information of that. And now the whole goal is to use some information theoretic classical procedure. And it's, as I said, is you basically do error correction and you do privacy amplification. And you have to show that both of these steps work even though an eavesdropper has quantum side information. So there's going to be a step where they compare errors, and they actually, there's some threshold, then say if the error is low enough, then we're good. Then Eve doesn't know too much about what has been communicated, and we can extract a secure key. Or they decide, oh, there were too many errors. So if somehow the error rate is above a certain threshold, they say, oh, we have to stop. We have to try again, because Eve might know too much about what has been communicated, and then you basically you have to restart the protocol. Yeah, so that's basically the high-level outline of how quantum key distribution works. And as I said before the talk, it can take up to a whole semester basically to learn a full security proof of that. Just because you need quite a bit of quantum information theoretic tools to model this. You need to kind of have min entropy about these strings, given some quantum side information, and then have to show that privacy amplification, like basically the leftover hash lemma, also works against quantum side information. You have to come with a proper security definition, etc. So it's quite involved to actually get a security proof of this.
I have one quick question.
Yes.
This almost looks like an OT protocol also, because Bob could just convey the places that he had the wrong basis and choose that as the set where he doesn't
Very
want
good. Exactly. That's exactly actually where I want to go to later in my talk. And I realize I'm already taking a lot of time, but maybe, I don't know, should I speed up? Because I can also go much faster, or just...
Maybe a little bit. I think some of us have to leave at the 1 hour mark, and
Okay.
some others beyond. So.
Okay. All right, and maybe, so this is a quick point that actually quantum key distribution you can actually do technically, because you don't need to do quantum computation. So there's no quantum computers involved. Basically, you can generate these photons and measure them upon reception. You don't need to store any quantum information. So that's why you can actually buy boxes that do this quantum key distribution. They look something like that. So there's just a optical fiber connecting them. And this is so far that, yeah, you can buy it, and therefore you can also hack it. So there's the quantum hacker that Vadim Makarov is famous for opening devices and destroying them. And he actually built an eavesdropping device that he took as a hand luggage through airport security to actually show kind of real life attacks on actual QKD systems. So, right. So this is as I said, kind of a three-party scenario, and I already described it. It's an advantage because you can show classically that you cannot do this. So now, I think the next thing I want to focus on is exactly that part with a two-party. So that's maybe the the thing I want to cover still in the time I have left. So I want to talk a little bit about two-party cryptography, and again in the setting with information theoretic security. So no computational assumptions. And the question is like, so we want to have protocols, and I guess you're all familiar with that are correct. So if both players are following the protocols, then it should do the right thing. But the same protocol should also be secure for honest Alice. So if she's following the protocol, but Bob tries to deviate, and the other way around. So if Bob is honest, but Alice tries to deviate from the protocol, she shouldn't be learning anything. And so here there's no eavesdropper. So it's just the move from two honest parties with eavesdroppers versus just two-party secure crypto. I guess you're familiar with that. So the things I want to talk about are coin flipping. So that's kind of in terms of usefulness, starting from the least useful to more useful, like bit commitment, then oblivious transfer, and two-party function evaluation. Where you can allow compute arbitrary functions. And from that, you can also get to multi-party computation, at least with a dishonest majority. And you are aware of that, these things, so I can go quickly here. So these are well known. So this is just classical. So far, no quantum. So if you have that, well, then you can also do multi-party and the other way around. And of course, oblivious transfer is just a special case of a two-party secure function evaluation, where Alice does not receive output and Bob just gets the bit of his choice. And if you have OT, you can do bit commitment. I think I'm going to show that quickly. And if you have bit commitment, you can do coin flipping. But not the other way around. So at least I think it's not known how to, well, here, correct me if I'm wrong, how to, if you have a coin flipping protocol, how to build bit commitment. It's also not classically not clear, at least maybe you can even show that you cannot do oblivious transfer based on bit commitment. But OT is complete. So if you have a model where you can do OT, then you can also do secure two-party computation. And so kind of the usefulness is in here. So oblivious transfer is kind of a nice measure of like, do we have a cool model? Do we have a model that is powerful enough to do OT? Well, then you can do everything else that you're interested in. Again, information theoretic security. So what I want to add here is quantumly, this implication is known. So you can actually, so that's again a difference between the classical and the quantum world. In the quantum world, you can upgrade bit commitment to oblivious transfer. And I'm going to show you how this works. So quantumly, somehow the usefulness is a little bit, it starts earlier. If you have a model that can do bit commitment, then you can also do the rest. So I wanted to start with coin flipping. Yeah, I think I have some time. Because there's also some quantum story here. So there's kind of two notions of coin flip. So there's the strong coin flipping, and that's maybe the regular thing. So no dishonest players can bias the outcome. So you want to make sure that even if you cheat in this protocol, then you cannot kind of bias the outcome towards one of the outcomes. And it's not so hard to see that classically a cheater, you can always obtain your desired outcome with probability 1 somehow. You could just kind of go back, and then there's always a way to kind of get to what you want. But there's a message that allows you to kind of win. Whereas quantumly, it's a bit different. So there have been protocols proposed that have a bias. So the bias is like how much you can go away from 1/2 of 1/4. And there's also been a proof of a lower bound by this, for this bias for strong coin flipping which is a bit below. And by now, so after a while, Xiaoyu and Karenese have come up with an optimal quantum protocol for strong coin flip, which actually achieves this bias. So in that sense, this is closed now. So we can have the best possible strong coin flip with that bias. Again, maybe in the spirit of Shafi's question, so like, okay, so what can we use this for? Yeah, so somehow kind of that's where it ends. So if you want to use if your goal is to do strong coin flipping, then we know how well we can do it. But yeah, I'll have a similar point to make on the next slide. Funnily, in the quantum setting, there's another thing which is called weak coin flipping. And so this is, you can always imagine as like who has to do the dishes. So somehow it's only like you really care about one outcome. No? So if, say, if the coin shows heads, then then Bob has to do the dishes, and otherwise Alice has to do it. And you really, Alice wants heads and Bob wants tails. And there's been a long story of Carlos Monchon, who kind of extracted ideas from Alexei Kitaev. It's like a quantum guy who doesn't like to write up stuff himself, but he needs kind of people who extract ideas from him. And he had this whole theory of point games. And in a series of paper, he ended up with a suggested protocol which achieves arbitrarily small bias epsilon for weak coin flipping. And these people, in like 7 years later, they managed. So this Monchon's paper has never been reviewed, and it's been more than I don't know 80 pages. So it has been reduced to 50 pages, but still not having an explicit protocol. But there's also been a bit of progress over the last years. Actually, people have come up with explicit protocols, even though they are pretty much numeric. So it's still kind of a mystery how this works exactly. But there are people in Jeremy Rolland's group in Brussels who have kind of figured out this in more details now. And the important, well, somehow you need these protocols to, for instance, achieve this strong coin flip. So this strong coin flip with this optimal bias, it uses this weak coin flip as a subroutine. So this all makes it quite complicated to run. So these are, I think nobody has been able to really implement this, but at least we have better understandings how these things now work. So that's for coin flipping. Then for bit commitment, of course, so you know what bit commitment is. So it has two phases. You want to commit to a bit. Say to Alice has a bit in mind, 0 or 1. And then in the first phase, you commits. In the second phase, you opens. And we want that Bob's point of view gives nothing away about this bit. So it should be hiding. Even if Bob is dishonest, he shouldn't learn what this bit is. And it should also be binding that Alice cannot change her mind anymore after the commitment phase. And classically, it's not that hard to see that this is impossible, because basically you can look at this yellow box here. So either it's information theoretically hiding, so it does not contain information about A, or it's information theoretically binding. It kind of determines A, but it cannot be the same at the same time. No? So that's basically why it's impossible to have classically secure bit commitment. And I see Oksana raised her hand. Did you have a question?
Oh, I had a question about the previous slide. So I didn't get the distinction between strong and weak coin flipping.
Maybe I just go back.
Maybe I can just ask you later.
Yeah, maybe in the interest of time I continue, but let's remind me afterwards. And quantumly, so funnily, people have thought that you can have quantum bit commitments, so quantum protocol for classical bit commitments, actually for quite a long time. So people thought, oh, but quantum is cool because you can actually do bit commitment. And so they've even published papers in Fox 93 about quantum protocols for bit commitment, but those turned out to be wrong because in 97 people realized that you can also not have bit commitment in the quantum case, and for a very similar reason. Basically, it's just information theoretically, either the information is there or it's not. And this is actually my suggestion, that if people want to study this, I think for this reading group, it might be great to actually look at one of these results, because it includes some very beautiful quantum techniques like purification and this Ullmann's theorem to just show the impossibility of bit commitment in the quantum case. It's something good to know, and it's also something nice to prove. So maybe if you can find some volunteer to do that, that would be great. Then, yeah.
Does it depend on which definition of bit commitment?
No.
You know, the impossibility. No, it doesn't. Okay. Mm-hmm.
No, it's very general. Okay. And people have over and over tried to kind of, but then maybe it doesn't take this into account or that into account. No, if you use the randomness from the stars, maybe then the impossibility doesn't apply. So, but this.
Okay. All right.
No, you really need some additional assumption to get bit commitment. Information theoretical. Well, so modulo relativity. If you start throwing in relativistic assumptions, then maybe you can do stuff. But without
quantum, thanks.
Yeah, if that's quantum, then not. And so here again, this is maybe for me one of the prime examples that if you allow some cheating probabilities, then you can do that in the quantum case. But these cheating probabilities are quite high. So they show that in any, so André Chaillot and Jordanis, they showed that in any quantum bit commitment protocol, one player can cheat with probability 0.739. And they also give an optimal protocol, again, based on this weak coin flip that achieves this. But so this is a very imperfect bit commitment protocol. And the question is, what should you do with this? So, okay, this is something that you cannot do classically, but also that's the end of the story. Somehow you have to be happy with that, because this does not compose at all, no? So you cannot use this to do something useful in any of your classical protocols because it has a huge error probability. So yeah, if you're happy with this as an end product, then great. But somehow calling this bit commitment in the sense of bit commitment, for me, it comes with this association, or it's quite a powerful primitive because it's often used in classical protocols to force people to be honest, etc. But that's only the case if it composes. If it has such a huge error probability, it will not. So this is really not. I don't know. I don't see much use of this kind of very imperfect classical primitives. So but of course, it's good to know that you can do it. Yeah.
This cheating probability cannot be reduced at all by sequencing.
No, because that's even in the statement. No, it shows that any quantum BC protocol, a player can cheat with that probability. So if you compose yourself, then it's still a BC protocol. And no.
Yeah. And so is the cheating sort of cheating for hiding or binding? As in, can I figure out what the bit is with probability 0.7, or can I break binding with probability?
Either somehow.
Okay,
so you can have one secure and then the other one isn't, or the other way around.
Okay, got it.
And this is kind of the trade-off point somehow where they trade. Okay. Now looking at the time. Oh, it's 2 minutes. What should I do? I think I should try to kind of get to the point here of the stuff that you don't know, because this is just showing how to do coin flipping from bit commit. This is the Blum protocol that you might have seen. I hope you have. So there's some kind of very cute information theoretic transformations between these primitives, and then Oblivious transfer. You also have seen in the various styles here. So maybe just kind of 2 quick comments about this. So this is standard Oblivious transfer, 1 out of 2 Oblivious transfer, 2 say, strings or bits as inputs, a choice bit. And funnily, this has been defined back in the very original paper by Stephen Wisner in '68. He has this example 1, a means for transmitting 2 messages, either but not both of which may be received. So kind of the very original definition of Oblivious transfer goes back to this paper. Of course, he had no idea that people would call this Oblivious transfer later on. So it has been rediscovered several times, and also with this name, and show the usefulness. But still, kind of that is exactly what you already had in this original paper. And yeah, so there's different variants. There's Rabin OT. People have realized that OT is symmetric. I think this is still my record of the shortest paper at Eurocrypt, or maybe at the crypto flagship conferences, just the realization that OT is symmetric. It only has 10 pages. I don't know if there's a shorter paper at one of the IACR conferences. And now what I want to show is basically what Dakshita said, namely the quantum protocol for Oblivious transfer, because it's exactly what you realized before. This almost looked like an OT protocol. So if you do what we did before in QKD, you basically use these BB84 states, this quantum key distribution state, send that, and then have Bob measure in a random basis. Then and do the same like basis exchange, then at this point you can simply make two sets of indices, namely where you measured correctly and where you measured incorrectly. And so imagine if you want to build Oblivious transfer, where now Bob has a choice bit and he wants to receive one of the two strings. What you can do is like just basically set the index set of the positions where he measured correctly as one set and the complement of it as other set. Tell these sets to Alice, she also forms these two sets, and then they basically apply some independent hash functions to kind of convert this raw key into some one-time pad key with which they can hide the secrets that they want to send, kind of the inputs to the OT. And also you basically just, Alice picks two hash functions, F0 and F1. She takes these strings and hashes them. You can even think of like to a single bit. And then she uses this as a one-time pad key to hide the bit S0 or S1 that she wanted to send originally, called this T0 and T1. And then of course, for those positions where Bob measured correctly, if he does the same and applies this hash function here, then it will recover that one-time pad key, and so you can recover the S1 bit that Alice wanted to send.
It seems extremely similar to the protocol by Crypto and Killian of how to use a noisy channel to do Oblivious transfer.
Yes.
It's almost identical.
Yes.
You are using this noisy channel comes out of the quantum. Yeah.
Yes. Yes. There, the noisy channel kind of provided the cryptographic resource that ensured the errors here. Here, it's the measuring kind of in the wrong basis. But of course, we are not quite done here. So this is just a suggestion of how the protocol works in the honest case. So let me see, we have to check correctness. So that's what I just described. If both players are honest, well, then it will work. But of course, we have to check security. And the easy case is security for honest Bob, so against the cheating Alice. So in that case, we want to make sure that Alice basically doesn't learn Bob's choice bit. At least in spirit, that's what we need to show. And the only message that Bob sends to Alice is this middle part. But this is just these are just random index sets, because he is honest, so he's picked his basis string at random. No matter what Alice has sent as basic string, these will be two random sets, independent of what his choice bit is. Maybe the order depends on his choice bit, but because they're random, Alice will not be able to infer anything from these two index sets. So that is the easy direction. The other thing is more tricky, because security for honest Alice, we want to make sure that an evil Bob, he cannot learn more than one of the bits that were sent. That's more tricky, because note what the dishonest Bob could do. If he is able to store all the qubits and simply wait until Alice tells him the right basis, well, then he can also obtain all the bits. He can just obtain the same string as Alice had. So if he's able to store these qubits for long enough until the basis arrives, well, then he also knows that string, and he can just recover the other bit as well. So we have to prevent him from doing this. And for doing that, there was the original suggestion of basically using bit commitment to basically force him to do these measurements. And the other suggestion, and that was part of my PhD thesis work a long time ago, is to use the so-called quantum bounded storage model. If you just simply assume that he cannot store all these qubits, well, then we're also in good shape. So I think I have a few more details about this, but then I can also stop. So here's the suggestion of how to use bit commitment. It's exactly the same protocol as before. It's just what you're gonna do. The beginning is the same. Alice sends these BB84 states. Bob chooses a random basis string. He does the measurement. But what he does now is he commits to the basis string and to the outcomes that he received. So basically, he puts those in a safe box. And before they go on, Alice does some checks. So Alice asks to open some of these positions, basically some cut and choose. So he opened some of these positions that, well, in this case, I was measuring a yellow basis, I got 0. Here I had the red basis, I got a 1. And then you can be, well, so those you have to get rid of, these positions. And then you can be pretty sure, or one has to show that that means that he basically also measured the other positions. And so you basically forced him to do a measurement there, and so to not just wait until the right basis is announced. So you can now announce the basis and then do the rest of the protocol exactly as before. So the rest is the same.
Great talk.
You have to go.
I do. Thanks. Sorry.
Okay.
So Christian, one
Yes.
question. So you can get a bit commitment from a one-way function, right? Some bit commitment from one-way function.
Mm-hmm.
So are you saying that one-way functions, let's say quantumly secure one-way functions,
Mm-hmm.
implies sublievious plus quantum, of course, quantum communication implies sublievious transfer?
I think so. So I mean, so how do you get bit commitment from the one-way function?
One-way function?
Oh yeah.
You can maybe one-way permutation. That's the easy thing, right? So I'm gonna to commit to a bit B. I pick a random string R. I send you one-way permutation of R, and then I pick the hardcore bit of R and XOR it with the bit. So that's hiding because of the hardcore bit.
Yeah.
It's binding because it's a one-way permutation. So you can't, I can't to reveal. I need to give you R, but I have, there's only one R.
Yeah. Everything is computational here, eh? So that's
yes, but all you need is a one-way permutation.
Right.
Whereas without the quantum communication, I would need some sort of like public key primitives and some bizarre things.
Right, but of course, so the question. So we studied everything in the information theoretic setting. So if you have, say, this works, if you have a UC bit commitment, then you're in shape and you can do
good
stuff.
Okay.
But the question is, do you even want to take the detour? You're saying you. Okay, so just from one-way permutation, you cannot get oblivious transfer in the classical case.
Yeah, exactly.
I see. I'm not sure if anybody has kind of fully studied that. So actually, Fang would be the no. In principle, I don't see the problem with this. Yeah. So quantum plus one-way permutations should probably give you OT. Yeah.
Yeah. Thanks. I have to sign off too. But
Okay.
Thank you very much.
Yeah, you're welcome. All right, maybe we should stop here. I don't know, it's recorded or so basically I think I was more or less done with this part. I mean, there was just the addition. Yeah, maybe I just show this one more slide and then the summary event, and then we're good. So the other option basically to get, again, to use the same protocol again and prevent dishonest spot from storing all the qubits is simply to wait. Because if you wait a second, 10 seconds, 1 second is probably enough, then nobody in the world knows how to actually store these qubits for such a long time. A long time, 1 second is a very long time for qubits to stay around. And that basically forces some measurement of the dishonest pop, and then you continue with the protocol. So you do the same as before. And so in this kind of limited quantum storage model where you're not able to preserve a quantum state for a second, one can also show, again, information theoretically that you can have bit commitment, but also oblivious transfer settings using exactly the same protocol. So as a summary, in this two-party crypto world, it's the added value of quantum here is the implication from bit commitment to oblivious transfer. That's something that we don't know how to do classically. And I think I will stop here today.
Thank you very much. That was a very useful and very exciting talk.
Thanks.
And we're looking forward to the next one.
Okay, so yes.
Does anyone have any questions? I think maybe we can take some questions.
Yeah, Oksana ahead, but now she's gone. Yeah, she's gone. I guess she was wondering about the difference between weak and strong coin flip. And so I guess in the strong case, you really want to make sure no one of the players can bias in either direction. Whereas in the weak coin flip, you really only care about one side. So one player cares for heads, the other cares for tails, and you want to make sure that they cannot bias towards that outcome. So it's in a sense easier to achieve.
Makes sense. Great. Any other questions? Okay, I'm going to stop recording now.
Okay.